Hello, and welcome to our Wednesday webinar from the International Center for Sustainable Carbon. My name is Benedicta, and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website, sustainable-carbon.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration on the website. Please type any questions in the questions box as we go along, and we'll answer them at the end of this webinar. The subject for today's webinar is the potential role of carbon utilization in a net zero economy, net zero emission economy, presented by Dr. Chen Su. Over to you, Chen.
Thank you, Benedicta. Hello, everyone, and welcome to today's webinar. In the next 30-40 minutes, I will talk about the potential role of carbon utilization in a net zero emission economy. Here is today's outline. I will give a brief review of the legal and the regulatory framework for CCUS in different countries and regions and the status of CCUS. I will then look at the recent development in CO2 conversion technologies and their applications. And this is followed by assessments of CCU's role in a net zero emission economy. And finally, the key messages from this study. As Benedict said, if you have any questions, please type them, write them down in the question box. And at the end of my talk, I will try to answer them. The United Nations have been raising the awareness of the climate change and the depletion of resources. The Kyoto Protocol was the first international treaty to reduce greenhouse gas emissions, which was signed by 192 parties in 1997. The Kyoto Protocol was superseded by the 2015 Paris Agreement. Paris Agreement is a legally binding international treaty that has been signed by 193 countries plus EU. At the heart of achieving the objectives of the Paris Agreement is the nationally determined contribution, or NDC, which is expected to be updated every 5 years by each country. As you can see from this slide, increasing number of countries are now resorting to CCUS to achieve their NDC. In America, Canada and the USA have developed comprehensive legal and regulatory frameworks and provided significant fundings for CCUS. This slide shows a brief history of CCUS policies that enacted in the USA. The EU and many European countries also host the most robust climate and CCUS policy mechanisms and the substantial fundings for research, development, and the deployment of CCUS, with new policies and the fundings are being announced continuously. For example, the Horizon Europe has a budget of 95.5 billion euros and runs until 2027 for research and innovation. and the EU Innovation Fund will provide around 10 billion euros over 2020 to 2030 period for the commercial demonstration of innovative low-carbon technologies, including CCUS. Policy is also advancing in the Asia-Pacific region. For instance, China has issued over 50 CCUS-related policies. However, regulations and the policies on climate and or CCUS are underdeveloped in other countries. There are several technologies for carbon capture. The post-combustion capture separates CO2 from flue gas after the fuel is burned. Pre-combustion capture converts the fuel by gasification into a syngas that consisting of hydrogen and CO2. Once the CO2 is separated, the remaining hydrogen-rich mixture can be used as a fuel or feedstock. Oxy-combustion capture involves burning a fuel in pure oxygen to produce a stream of CO2, which is ready for sequestration. And direct air capture extracts CO2 directly from the atmosphere. CO2 conversion covers a wide variety of technology pathways, including chemical, electrochemical, photocatalytic, photosynthetic, biocatalytic, and biological process, and the carbonation. The figure in this slide shows the project pipeline for commercial CCUS facilities since 2010. After years of slow progress and insufficient investment, the recent new policies, investment incentives, and higher climate targets are building new momentum behind CCUS, which is growing rapidly, especially in the past 2 years. The table underneath gives a list of the number and the total CO2 capture capacity of commercial CCUS facilities. Increasingly, the focus for the application of CCUS is in the industrial or hard-to-abate sectors. Despite the recent acceleration, CCUS is still in the early stage of technology and the market development. CCU is a valuable commodity. It is widely used directly for enhanced oil recovery in beverage carbonation as a coolant, a fire extinguisher, and so on. CO2 can also be used as a feedstock for production of a wide variety of commercial products, including fuels, chemicals, polymers, and building materials via multiple chemical and biological processes. CO2 can be combined with hydrogen to synthesize hydrocarbon fuels that can replace many of the fossil-based fuels available on the market today, such as methane, methanol, gasoline, and aviation fuels. CO2 can also be used to make chemical intermediates, including syngas and methanol for production of other chemicals. There are many technical routes for CO2 conversion, many of which are still in early stage of development, but some conversion technologies are mature. The most mature conversion pathways are direct conversion or hydrogenation of CO2 in the presence of hydrogen into methane or methanol, and the indirect conversion of CO2 via reverse water gas shift or RWGS into carbon monoxide, followed by Fischer-Tropsch process or methanol synthesis process. The development in effective catalyst and advanced reactor design for CO2 hydrogenation have resulted in commercial plants being operational or being developed in several places around the world. For example, the CRI of Iceland has been producing methanol commercially since 2012, using CO2 captured from a nearby geothermal power plant and recycling 5,500 tons CO2 annually. The methanol produced is used as a blend component of gasoline and for further conversion to a diesel substitute. Last year, the world's largest CO2 to methanol plant started operation in China using the CRI's technology, capturing and converting 160 kilotons CO2 per year from existing lime production emissions to produce 110 kilotons of methanol. A second plant is under construction in China and is expected to come online later this year. This plant will recycle around 150 kilotons of CO2 to produce 100 kilotons methanol each year. Another plant using CO2 captured from the emissions of a ferrosilicon plant and the electrolytic hydrogen powered by renewable energy is under development in Norway. This plant will recycle 150 kilotons CO2 per year to produce 100 kilotons methanol using the CRI's technology. CO2 hydrogenation processes have been developed by other companies and reached commercialization or demonstration stages, with several commercial projects under development or having been announced. The RWGS plus Fischer-Tropsch technology has been investigated more extensively, and some processes have reached commercialization stages. This slide shows the first plant in the world to produce fuel oil for synthetic kerosene, approved by the ASTM for commercial aviation. Several companies are currently marketing their technologies, with some major commercial projects being developed. And this slide and the next shows the selected major CO2 to fuel projects operational or under development globally. As you can see, that most of the projects are being developed in Europe. In recent years, there have been significant breakthroughs in bioconversion of CO2 to fuels, and the several systems such as the LanzaTech's fermentation process electrification two-step biomethanation process, and the Hitachi Zosen Innova's biomethanation process known as BION have been developed and are now commercially available. This table gives a list of the commercial projects in operation or under construction that use LanzaTech's process. CO2-based polymers are already commercially available from traditional suppliers and the startups using innovative approaches. Polymers can incorporate up to 50% of CO2 by weight, and they can be used to produce a wide variety of products used in our daily life. The catalytic conversion is the most mature technology, whilst bioconversion processes are emerging. Today, CO2-based polymers are already sold on the market, and this slide shows some of the commercial products from CO2-based polymers developed by various companies. These slides give a list of commercial plants worldwide that produce CO2-based polymers via catalytic conversion. Commercial products based on bioconversion of CO2 have also emerged into the market. For example, New Light Technologies has launched two brands, Restored Footwear and Covalent Fashion, which are based on a degradable biomaterial produced by bioconversion of CO2. Some electrochemical conversion processes for CO2-based polymers production have been successfully demonstrated as well. The market for building materials from a combination of industrial waste with captured CO2 and CO2 cured concrete has developed rapidly in the past few years. It has been shown that CO2-derived aggregates and concrete products can have properties similar to or even better than those of conventionally produced counterparts, and hence can be used for the same applications. Various processes of CO2 carbonation of waste for production of aggregates and other building materials have been developed, and several commercial plants are in operation around the world. And this slide shows some of the products and the technologies being offered to the commercial market. Concrete is the most widely used material in the world after water. CO2-cured concrete is found to have similar or better performance, lower costs, and lower CO2 emissions compared to conventionally produced concrete. A group of companies are supplying various CO2-cured concrete products or technologies on the market, and a number of CO2 curing processes have been adopted in concrete production facilities. For instance, the carbon cure process has already been installed in over 400 concrete plants in North America, Asia, and Europe. More companies are commercializing their products or technologies. Most of the processes use pure CO2, but some, such as the carbon-8 ACT process, the green oils process, can use low-grade CO2 or flue gas coming directly from industrial processes or power plants, which has the advantages of capturing and utilizing emitted CO2 in one system and significantly lower the overall costs. Several studies indicate that almost all the CCU products discussed above potentially have lower life cycle emissions compared to the traditionally produced counterparts. This slide shows the analysis results from the IEA greenhouse gas projects. The number in the gray circles represent the carbon emission reduction can be achieved by substituting fossil-based methanol and other fuels with CO2-derived counterparts, CO2-derived relevant under different scenarios. Thus, CCU can contribute to emission reduction as it can be used to displace fossil-based fuels, chemicals, and conventional building materials that have higher life cycle emissions. In addition, CCU offers versatile and practical solution for emission reduction in hard-to-abate sectors where alternatives are technically limited. It also facilitates the use of renewable energy and offers co-benefits of energy storage, and hence contributes to emission reductions as part of a portfolio of clean energy technologies. Therefore, CCU has the potential to decarbonize power, transport, and other industrial sectors and generate revenues through marketable products. The climate benefits of a CCU product depend on many factors, including the scale of its application, the life cycle emissions of the product it is to displace, and the source of low emission energy used. A host of technologies for converting CO2 to synthetic fuels, chemicals, or polymers and building materials have been developed, with several successfully implemented technologies are now in commercial use. This slide shows the potential CO2 demand by different CCU products estimated by the International Energy Agency. It shows that CO2-derived fuels present the greatest market potential with annual demand for CO2 of over 5 gigatons. Building material and the chemical intermediates can generate a CO2 demand between 1 to 5 gigatons per year, and the CO2 demand from polymers is less than 1 gigatons per year. There is a considerable interest in CO2-derived synthetic fuels for aviation and shipping sector. For synthetic fuels, there is greater political and regulatory support for sustainable products, with some regions, such as the EU, introducing mandates or new standards for the use of sustainable fuels. This could increase uptake of CO2-based fuels in those regions. Despite the significant potential, the growth of demand for CO2 is limited to the anticipated market size of the CCU products. Due to many uncertainties, the estimated global CO2 demand by CCU is wide-ranging from 1 to 7 gigatons CO2 per year in 2030. The most optimistic figure of 7 gigatons CO2 per year equals to nearly 20% of the global CO2 emissions today. This is significant, but obviously it is not adequate for climate change mitigation. So CCU is not expected to deliver the emission reductions on the same scale as other options, such as carbon capture and storage. However, CCU can play a supplementary role as part of the all-technology approach in meeting today's energy and climate goals. As to the competitiveness of CCU products, in most cases, CO2-based fuels and the chemicals are found to be considerably more expensive than their fossil-based equivalent, as shown in this slide. Therefore, supportive policies and incentives are vital to its widespread deployment. CO2-derived polymers could be produced at lower cost than their fossil counterparts, but the market is relatively small. CO2-based building materials can be competitive today and have greater potential on the existing market drivers. The CO2-based building materials show greater environmental benefits than other CCU products, as they can lock up CO2 permanently. In addition, CCU can generate important income to offset carbon removal costs and providing a low-cost decarbonization solution in some sectors or regions. It also provides a new source of essential carbon feedstock in a circular economy. So this leads to our key messages today. CCU can be used as a supplement to other technologies and measures and play a vital role in our efforts to achieve net zero emission and in a circular economy. There are a number of pathways to convert CO2 into a range of valuable commercial products, and several technologies are advancing towards maturity and are increasingly found in commercial applications. Almost all CO2 conversion pathways exhibit potential for lower life cycle emissions compared to conventionally produced products. The opportunities for CCU are significant, with potential applications spanning various sectors. CO2-derived fuels present the greatest potential scale for deployment, followed by building materials and chemicals. CO2-derived fuels and chemicals are more expensive than fossil-based counterparts, whilst CO2-derived polymers and building materials can be competitive in today's market. So supportive policies are critical to large-scale deployment of CCU. And this is the end of my talk. Thank you very much for your attention. Now let's see if there are any questions. Right. The question is, presuming the slides will be available to attendees afterwards, as always. Yeah, it is. It will be available. Right. There's another question here. The CO2-based fuels and the chemicals are much more expensive than the fossil fuels. How can its use make a business case? For CCU products that are not competitive today, the regulatory and the policy measures and incentives are required. Take the sustainable aviation fuel as an example. The EU law stipulates that from 2025, all flights departing from EU airports must have a minimum share of 2% of sustainable aviation fuels. That percentage will rise to 6% in 2030 and to 70% by 2050. So this is a mandate that all airlines have to comply with. This is the main driver behind the development of several major commercial CO2-to-fuel projects in Europe. All these projects have received or are applying for fundings and financial support from the EU and the local government. However, because the high cost of sustainable aviation fuels, a financial mechanism and the incentives and other supporting policies are needed. The EU is currently considering the tax credits, something similar to the USA's IRA, the Inflation Reduction Act, for investors and developers, but much more is required. Oh, we got quite a few questions here. The other one is, the CO2 in the CCU product will be re-emitted back into atmosphere when the product is used or at the end of its life. So it only delays the emission rather than reduce it, isn't it? Well, that's not true. Carbon is a commodity for producing many products essential to our everyday life. Even in a zero emission economy, carbon will still be required in some applications. Also, there will be some unavoidable emissions in the foreseeable future, such as the emissions from aviation, shipping, gas-fired power generation for stabilizing the grid, and some bioprocesses. CCU recycles the emitted carbon and helps to close the carbon loop and create a circular economy. Although some CCU products only store the CO2 temporarily and the CO2 will be released back into the atmosphere when the product is used or disposed of. You have to remember that this CO2 is captured and reused. Using the captured CO2 prevents the use of fossil fuels and the related emissions. For each carbon molecules is being used twice. For example, the CO2 from fossil fuel use is captured and then combined with hydrogen to produce a synthetic fuel using renewable energy. And when the fuel is used, eventually the CO2 is re-emitted back to the atmosphere. But this, from the energy system perspective, there is a maximum emission reduction of 50% can be achieved. If the biogenic CO2 or CO2 from direct air capture is used, then the life cycle emissions of the synthetic fuel can be minimized. So in theory, in principle, the cycle of capturing and reusing the carbon content in various waste or products at the end of the life can be repeated. So therefore, the CCU can become a part of a circular economy and a form of sustainable waste processing. Right. Next question is, next question is, what is the level of interest from the aviation sector for CO2 syn fuel? Well, because there's a EU law on the minimum level of of aviation fuel in from 2025, so there is significant interest in producing synthetic fuel using captured CO2. There are quite a few commercial projects under development now to producing aviation fuel in the Europe, and some project in the USA, in America, and other countries, South America as well. Oh. Sorry, I've lost the. Okay, it's come back. Yeah. Next question. Is there a cost estimate of scaling up the process for commercial operation? I'm not sure which cost estimate scaling up the process. I assume you meant for fuel production, commercial operation of fuel production. For the for polymers and the building material production. I think there's already quite a few commercial plants in operation, and that because the costs are competitive, there are some because they are already in operation, so there are some analysis of costs. But I don't have that numbers in my head now. But for the fuel productions, there are a lot of studies into this, but it varies, depends on the assumptions used. For people interested, you can refer to my report. There will be some information there. Let's move to the next question. Compared to CCU with biochar from pyrolysis process, which one will be the most effective in reducing carbon emissions and the more variety products? Oh, I'm sorry, I haven't looked into this, so I don't know. I don't have an answer for this question. And the next one, unfortunately, I couldn't hear your voice in the last 10 minutes, although this may be my PC. Oh, I'm sorry. But the webinar will be available on demand, so you can listen to it later at your convenient time.
Super. Thank you so much, Chen. I think that's all we have time for today. And as you said earlier, the slides from this webinar will be available to download from our webinar page shortly. And thank you all for joining us today, and goodbye.